Hey guys, today we will take a look at the 3D camera for the second time. I already have 3 videos on this topic and I've used my own math code to make them. But many people have asked me for an implementation using the highly popular GLM library. In general, I consider 3D math to be a core part of 3D graphics, and I believe it's critical to have absolute control of this topic. This is why I always recommend beginners to implement the math part on their own, at least once. Okay, to make a long story short, as I'm making my way through the 3D graphics rendering cookbook for my Vulkan series, I came upon a chapter with an implementation of the 3D camera using GLM, which is quite different from my own, and I decided to make a video about it. We will use this implementation today in an OpenGL demo, and the exact same code will be used later on for Vulkan as well. Okay, before we get started, I'd like to say a big thank you to Gonzalo, who recently joined the 3D Underground. If you too would like to support this channel, you can do that at patreon.com/ogldev or by joining the YouTube channel as a member. Now I'd like to recap a bit, just in case this is your first time with this material. What exactly is the 3D camera? It is a software component which provides the VP in the WVP matrix. WVP is of course the combined matrix, which takes a vertex from local space to world space, to view space, and finally to clip space. VP stands for View and Projection Transformations. The view space transformation reorients the world so that the camera is sitting at the origin and its target vector is aligned with the z-axis. For a left-handed coordinate system, this will be the positive z-axis, and for a right-handed coordinate system, this will be the negative z. Naturally, after applying this transformation, the orientation between the camera and any other object in the scene remains the same. The view space transformation sets the stage for the projection transformation, which projects all the objects within the view frustum on a square which goes from -1 by -1 to 1 by 1. For more details on these two transformations, check the 3 videos that I've mentioned, as well as the 2 videos on the projection transformation. See the links in the video description. But this is not the end of it. The expectation is that the camera will be dynamic within the scene, which means that the user will be able to control it using the keyboard, mouse, gamepad, or whatnot. So the transformations must be recalculated for the dynamic changes in the state of these controllers. Okay, let's build the camera. The first step, of course, is to get a copy of the GLM library. This is very simple. Just go to their GitHub page, clone the repo, and place it somewhere that makes sense for your project. Note that GLM is a header-only library, which means that the entire implementation is contained within HPP files, which must be included in your sources. There is no lib file that you need to link against or a DLL for running the application. I try to make my sources run out of the box as much as possible, so I've included a copy of GLM under ogldev/include/GLM. I may update it every once in a while, but it will be best for you to simply get it from the origin. Next, we need to make sure that our build system can find the GLM files. If you're using Visual Studio, then right-click the project, go to Properties, C, C++, and General. In the additional include directories, add the path of the folder that contains the GLM source tree. In my case, it is the relative path to ogldev/include, but it will probably be different for you. If you're using any other build system, simply make the necessary changes. We can now include GLM in our sources. In the new header for the GLM camera class, I've included glm/glm.hpp and glm/ext.hpp. This will cover everything that we need for this tutorial. For other services of GLM, more files may need to be included. Now let's create a class for the camera called GLM Camera First Person. As a first step, this class will include 3 private attributes: a 4D matrix for the perspective projection transformation. This is of course P in WVP. A 3D vector to maintain the camera position in world space. And finally, a quaternion to maintain the camera orientation. Quaternions are out of scope for this tutorial. In a nutshell, they provide a convenient method for handling rotations in 3D space. Luckily for us, GLM provides various methods for calculating quaternions, so we just need to make ourselves familiar with the API. We now need to create a few public methods. The constructor takes the position of the camera, the target, an up vector, and the perspective projection information. The three vectors are in world space. The target actually represents a point, so to calculate the target vector of the camera, we need to subtract the position from this vector. The up vector simply shows the up direction of the camera. If the camera is your head and your eyes are looking straight along a vector, which is roughly parallel to the ground, then the up vector simply continues the direction of your body towards the sky. Turning your head in this case will not change the up vector, but if you tilt your head to the side, then the up vector will follow. In most cases, the up vector will simply be 0, 1, 0. The flight simulator is a prime example of a case where the up vector can point pretty much anywhere. The perspective projection info structure contains everything that we need to calculate this transformation. This includes the field of view angle, the width and height of the window, and the depth of the view frustum from Z near to Z far. The class will contain a couple of getter functions to get the perspective projection matrix, as well as the position. There are also two functions that return the view transformation and the combined view and projection transformations. These functions are more complex, so their implementation is in the CPP file, which is where we're going next. The job of the constructor is to set the initial value of the camera orientation quaternion and the perspective projection matrix. I've decided to support both left and right-handed coordinate systems, even though in my videos I only use the left-handed system. So I've included a Boolean flag in the header called camera left-handed. GLM actually provides a pre-processing macro called GLM force left-handed, but I found it to be somewhat unstable, so I decided to keep GLM in its native form, which is right-handed, and call the explicit functions for each case. So instead of lookat and perspective, I use lookat LH, perspective LH, and lookat RH and perspective RH. The lookat function takes the position, target point, and up vector and calculates the orientation quaternion. The perspective function takes the field of view, the aspect ratio, which is the width divided by the height of the window, Z near and Z far. We can now implement the function that calculates the view space transformation. This transformation is twofold. First, we need a translation matrix to move everything in the world so that the camera is sitting at the origin. This matrix must be multiplied on the left by a rotation matrix, which aligns the target vector of the camera with the z-axis. For the translation matrix, we use the GLM translate function. The first parameter is the identity matrix. This function allows you to start the matrix from an existing transformation, but we want a clean slate, so we start with the identity matrix. The parameter is the position of the camera in the negative. So if the camera is at 1 by 1 by 1, we need to move everything by -1, -1, -1 to get the camera to the origin. For the rotation matrix, we simply convert the quaternion to a matrix using the mat4cast function. The quaternion represents the coordinate system of the camera using world space vectors, and the matrix representation of these vectors is exactly what we need. If you need more details on this subject, then I have a video from Rome, Italy on exactly that. We multiply the two matrices together to get a final view space transformation of the camera. The function getVP matrix simply multiplies the view matrix by the projection matrix. Notice the order. First view and then projection. In the vertex shader, you must multiply the vertex position on the right-hand side of the VP matrix. So we have the position transformed to view and then projected. We are now ready to test the first implementation of the camera. In the application code, we add a pointer to the GLM camera first-person class, and we allocate the object using some parameters for the position, target, and up vectors, and the projection information. In the render function, we get the view projection matrix from the camera object. The infinite grid class is what renders the nice grid that we see here. It needs the VP matrix as well as the position of the camera, which we provide. Notice that we don't need a world matrix here because the grid is considered to be already in the world. In a standard 3D application, you will probably need to calculate the world transformation matrix for each object and multiply it on the right-hand side of the VP matrix to get the final WVP matrix for your vertex shader. So this looks okay. We can play with different parameters and make sure that everything is working correctly. The next step is to make the camera interactive and control it using the mouse and keyboard. We will start with the keyboard because it is a bit easier and we'll set some base code for handling the mouse later on. To detect keyboard input, we use the GLFW library, which I've been using for most of my tutorials, so you are probably familiar with that. As far as I know, this is the most popular option for this sort of task. There are other options, of course, such as FreeGLAT, SDL, SFML, and etc. SDL and SFML are actually frameworks, but they provide their own mechanisms for mouse and keyboard control. It will be a good architecture if we can separate the camera code, which is mostly math, from the keyboard control mechanism. For this, we add a structure called camera movement, which encapsulates the basic motion options of the camera. Each attribute in this structure is a Boolean flag, which indicates whether the specific movement is currently in effect. We add an instance of this structure to the camera class. It's in the public section for easy access. As usual, the application class contains a function that handles the keyboard. This function is called from the GLFW keyboard callback function, which is registered by GLFW setKeyCallback. To make things as reusable as possible, I've added a function called GLFW camera handler in a common file which contains most of the code that deals with GLFW. This function takes the camera movement attribute from the camera object, as well as the parameters of the keyboard callback. Notice that camera movement is passed as reference, because this function is going to update it. What we have here is simply a big switch case statement, which translates the common keys, such as WASD, etc., to the corresponding attribute in the camera movement structure. The Boolean value which is set into the structure indicates whether the key is pressed. In GLFW, when you press a key, you get two notifications. The first notification is that the key was pressed, and the second that it was released. So we will set the attribute to true and then back to false. In the main render function, we call a new function in the camera class called update. This function takes the delta time from the previous iteration of the main render function. It's very easy to calculate. I use a function called GLFW getTime to get current time, and I subtract the time from the previous iteration. After calling the main render function, we update the current time. We need the delta time because the speed of the camera is dynamic, and we want to move the camera based on the elapsed time from the previous update. Talking about speed, let's add a 3D vector as a private attribute of the camera class and call it velocity. This vector encapsulates the direction that the camera is moving, as well as its speed. The speed is simply the length of this vector. We also need a few configuration parameters. Again, let's put them in the public section for easy access. First, we have an acceleration factor, which is used to scale up the change in velocity. Damping is a common term in physics, which describes the loss of energy in a system. This can be the result of friction and any other type of resistance. We will use it to slow down the camera once a key is released. This looks much nicer compared to when the camera is stopped abruptly. Next, we have the maximum speed. When a key is pressed and then held, the camera accelerates. This value prevents the camera from reaching the speed of light. And finally, we have the fast coefficient. When you press Shift along with one of the direction keys, the camera gets another boost on its acceleration. This attribute defines this factor. If you don't need this feature, feel free to drop it. Now let's take a look at the update function. What we do here is to calculate the velocity and then update the camera position by adding the velocity vector multiplied by the delta time. This way, the camera should behave the same regardless the speed of the machine or the frames per second. Now let's see how the velocity is calculated. To do that, we first need to calculate the acceleration. This is not a video about kinematics, so I'll just say in a nutshell that velocity is the change in position in a given period of time, and acceleration is the change in velocity in that period. When a car is going at a constant 60 miles per hour, the velocity is 60 miles per hour and the acceleration is 0. The speed of the car doesn't change. To get from 0 to 60, there has to be a non-zero acceleration, which increases the velocity. The acceleration is also a vector whose direction depends on the key which is pressed. To calculate it, we start by converting the orientation quaternion to a matrix. Again, the GLM function matForecast is used for that. This matrix provides us with the world-space axis of the camera in its current orientation. GLM uses column major matrices by default. This means that the right vector of the camera is in the first column, the up vector is in the second column, and the forward vector is in the third column. As you can see here, the up vector is actually calculated as a cross product between the right vector and the forward vector. This is the original implementation from the book, and I'm not sure why they didn't simply extract the up vector from the matrix. I tried both methods and they seem to behave in the same way. Anyway, be careful about the forward vector. When extracting it from the matrix, it must be negated for a right-handed system. Otherwise, you will move backwards instead of forward. This part is always confusing, and while the code works for both coordinate systems, there may be a way to write it in a more natural way. Let me know what you think in the comments below. Now that we have the three axes of the camera, we can update the acceleration according to the activated directions. Note that each direction is checked and the corresponding vector is accumulated into the result. This allows us, for example, to press both forward and right at the same time, and the camera will move in diagonal. If the fast speed key is pressed, we scale up the acceleration by the corresponding coefficient. Now that we have the acceleration, we can calculate the velocity. If the acceleration is 0, it means that no key is pressed, and we need to gradually decrease the velocity. For this, we use the damping parameter. The higher the value of damping, the faster the velocity decreases. We multiply damping by the delta time and take the minimum between the result and 1. This is multiplied by the velocity and then subtracted from the velocity. For example, if damping is 5 and dt is 0.016, which is roughly 60 fps, we decrease about 8.5% from the velocity of the previous frame. The following graph shows how the velocity is decreased from the default maximum speed of 10 over time. You can play with different damping settings and see the effect. The case of positive acceleration is even simpler. We just need to add the acceleration vector multiplied by the acceleration factor multiplied by the delta time. The configured acceleration factor determines how fast the camera accelerates. The next few lines of code make sure that we don't go over the maximum speed. You can see that when the fast speed key is pressed, we actually allow the maximum speed to be even higher. Remember that after calculating the velocity, we add it to the camera position after scaling it by the delta time. The last thing that we need to do in this video is implement mouse control. We add a small structure to maintain the state of the mouse. It contains a 2D vector for the position of the mouse cursor and a Boolean flag that indicates whether the mouse button is pressed. The camera doesn't care whether this is the left, right, or the middle key. This is up to the application to decide. It only cares that the designated camera button is pressed. We add the mouse state as a public attribute of the class, same as the keyboard movement. We also add a configuration parameter to control the speed of the mouse. In the private section, we add a 2D vector for the old mouse position. This will help us calculate the delta between two calls to the camera update function. Let's see what we need to do on the application side. There are two GLFW callback functions that we need to implement. Mouse move is called when the mouse cursor is moved. This function is registered using GLFW setCursorPause callback. It gets the x and y position of the mouse cursor as integers. We want the camera code to be agnostic to the window resolution, so we divide x and y by the width and height of the window, respectively. We also cast everything to floating point, so we get a fraction between 0 and 1. The result is set directly into the mouse state attribute of the camera. The mouse button callback is registered by GLFW setMouseButtonCallback. We check whether the function was called for the left button, and we set the button pressed flag in the mouse state according to the action parameter. True if this is GLFW press, and false otherwise. Now let's go back to the camera update function. We start by checking whether the button is pressed, and if it is, we call a new function to update the camera orientation. This function starts by subtracting the old mouse position from the new one. This gives us the delta mouse movement. This is a 2D vector, which can point anywhere. Now let's think about what we're trying to accomplish. When the mouse cursor moves between left and right, only on the x-axis, so the delta y is 0, we want to turn around the up vector of the camera. Remember that in general, the up vector can point anywhere. In GLM, we need to create a quaternion to turn around the 0, 1, 0 vector, which is the up vector in the camera local coordinate system. We multiply it by delta x to match the amount by which the mouse moved along the x-axis. When the mouse cursor moves up or down, only on the y-axis, so delta x is 0, we want to turn around the right vector of the camera. Again, the right vector can point anywhere. The quaternion this time needs to turn around 1, 0, 0 by delta y. What's nice about quaternions is that we can combine the two quaternions together into a single quaternion to handle movements on both x and y. We also multiply it by the camera speed to control how fast the camera turns for each pixel that the cursor moves. We multiply this local space quaternion by the camera orientation, which is also a quaternion, and this rotates the world space coordinate system of the camera according to delta x and delta y. Remember to normalize the result. We want the axis of the camera coordinate system to be unit length, aka orthonormal coordinate system. And we have to save the new position of the mouse for the next call. The code can now continue as usual. Remember that the function that calculates the acceleration starts by extracting the axis of the camera coordinate system, so this system is now updated for the latest movement of the mouse. Now let's do an experiment. I'll disable the update of the Y position of the mouse. You can see that the camera turns correctly around its up vector, and any change in Y is ignored. We do the same with x, and the camera turns around the right vector. But when both x and y are updated, we see that eventually the camera starts behaving like an airplane. This is because the changes in x and y starts accumulating, so the up vector no longer points directly up, and the entire coordinate system starts behaving like, well, an airplane is the best example. If this is the behavior you're shooting for, that's great, but in many cases we want to turn the camera while avoiding tilting it from side to side. To fix it, we add a private attribute to the camera class to store the original up vector. We save this vector in the constructor. At the end of the function that calculates the orientation of the camera, we call a new function to restore the original up vector. This function extracts the direction the camera is pointing from the view matrix. Same as before, this vector is located in the third column of the matrix. We reconstruct the camera orientation quaternion using the same lookat function that we used in the constructor. The camera position hasn't changed. The target point is calculated by adding the direction of the camera to its position, and the up vector is always the original one. So only the direction can change, but not the up vector. In airplane terms, this means that the camera can yaw and pitch, but it can't roll. And that's it for today. Let me know what you think about this implementation and whether your camera is different. Thank you for watching, and I'll see you next time.